All right, so like I said, we're going to kind of continue on here in chapter 5. Also, a reminder as well, as mentioned, we will be taking a quiz at the start of lab, again, basically on bonding, geometry, everything. And the kind of chapters, I guess it would be 3 and 4, sounds like, I think, the right ones. Okay, so where we left off was talking about formulas, really. Well, before that, we sort of talked about a couple of important sort of conversions that we do a lot here in chemistry. In addition, we talked about atomic mass before that and how they sort of came about it on the periodic table. But here we also talked about molar mass. And molar mass, remember, has units of grams per mole. And we do get that from the periodic table, basically adding up everything that's there in the actual formula. Also, really important, when we do molar mass, especially later on when we start doing things like stoichiometry and stuff like that, and we use a balanced equation, that whenever you're asked to sort of do the molar mass or get the molar mass of a particular substance, you should always do it based off of the actual chemical formula, just one of the chemical formulas. So, what I mean by that is, again, in a later chapter, uh, obviously might be dealing with some balanced equations, and perhaps maybe you have like a three waters or something like that, and you need to do an equation, obviously, and you want the molar mass of water. And very common people will actually include the 3 here when they go to do the molar mass, and that is incorrect in terms of molar mass. If you were asked to do the molar mass, regardless if there happen to be 3 of them in an equation or something like that, you should just do it solely based on the actual formula. And that's because the definition basically of molar mass is how many grams there are in 1 mole of the particular substance, and 1 mole of any substance will basically be the chemical formula. So that's a good thing to keep in mind, especially a little bit later on when we get into stoichiometry. Sometimes people kind of take the coefficient as well, and then they take the coefficient for the stoichiometry part, and before you know it, they end up with sort of the wrong answer when it's all said and done. So when you go to the periodic table, you want to calculate molar mass. It is done based solely on the formula. That's how many grams there are in always 1 mole. So the mole never has a number in front of it. It's always the grams part that has a number. And most importantly, though, really we use the molar mass as a conversion factor to go from really grams to moles or backwards. So that is the conversion factor that we use basically to do that. We can divide by the molar mass, and that gets us moles. We can multiply by the molar mass, and that gets us grams. In addition, the other kind of important number we talked about was sort of Avogadro's number. And Avogadro's number is there's 6.022 times 10 to the 23. These could be atoms. These could be molecules. They really could be kind of any unit you like in 1 mole of something. And this, again, is something that we use really as a conversion factor to go between our moles and atoms or moles and molecules, and back and forth in terms of that. So again, we do a similar type of calculation using this as sort of a conversion factor. If we had moles, we would multiply by Avogadro's number up on top. And again, you would end up with either atoms or particles or molecules, depending on obviously what you are starting with. Or obviously, if you are starting with atoms or molecules or something like that, we would divide by Avogadro's number there. And moles would go up on top, and you would end up with moles, as these would be atoms. That looks like a really bad 23 there. I'll try that again, fix that up. Again, obviously the atoms would cancel, you'd be left with moles. Important that we also talked about was the idea that even though you know Avogadro's number, don't use Avogadro's number in every calculation. You should only use it when you mention something about atoms, molecules, or something like that, or you're asked to find something in atoms, molecules, particles. Again, no mention of it, then don't use Avogadro's number. Also, as well, when we see MOL, that is again the abbreviation for moles, not molecules. So again, that's a very common sort of error that people make. We also sort of talked about, formulas and how to calculate certain types of formulas. One type of formula is the empirical formula. And that really is the simplest whole number ratio of what's present. And to calculate the empirical formula, there's basically a few steps. First off, if you have that percent composition, you want to convert it into grams. We could assume 100 grams is an easy way to do that. You want to then convert the grams to moles using the molar mass from the periodic table. You want to divide by the smallest number of moles. And if you do that and you divide all the moles by the smallest number and you hit whole numbers, then you have your empirical formula. You're good to go. You're done. If you don't get a whole number, as we talked about last time, you might sometimes have to multiply by a common number in order to get to a whole number. So, for example, I think maybe we use something like a b 2.5. Again, here that's not a whole number, but if we multiply not just the last guy by 2, but the entire thing by 2, gives us the proper empirical formula of A2B5. So again, if it's really close to a whole number, like 0.99, 0.0 something, just over a number, those are probably areas where you could round. If you typically end up with a number when you're dividing that's like 0.33, 0.25, 0.50, something like that, these are probably too far to round, and you need to find sort of, again, a common number that will allow you to do that. The other type of formula we talked about is a molecular formula, and we'll talk more about that one today as well. But the molecular formula is essentially the exact amount of everybody that's present. So again, molecular formula is C2H4, like we talked about last time. That basically is a 2 carbon to 4 hydrogen ratio. And if we wanted to get the empirical formula from that, that would also reduce down to 1 carbon for every 2 hydrogens. The empirical formula would be something like CH2 in this particular case. So, you can sort of, if you're given a formula and you can reduce down, again, everybody by a common number to hit a whole number, then you can get to the empirical formula. As we also saw last time, for example, something like water, that is both the empirical and molecular formula, as you can't pretty much reduce it down any further. Any questions on any of those things we talked about last time? Okay, so what we're going to talk about next is another type of empirical formula problem, one that's a little bit different than the one we did before or just talked about over here. And it's a little bit different of a method to calculate the empirical formula. And let's talk about how to kind of go through that. And it's a reaction that is done, which is basically a combustion reaction. And this is a common sort of procedure that is used, especially when we're dealing with some type of organic compound. And basically what an organic compound is carbons, hydrogens, and oxygens. And it's a combustion reaction, which means we have some O2, and we always make CO2 and water is produced. Also, usually we get a lot of energy, sometimes some flame coming out in a reaction such as this. But by taking this organic substance, which we know for sure, does contain sort of these three elements, we can put it through sort of this reaction, and we could collect a couple of things on the back end of this reaction, which are we could collect the amount of CO2 that we produce in this reaction. We could also basically collect the amount of H2O that we get in this particular reaction. So why is that important to sort of collect those? Well, it has a lot to do with the idea of conservation of mass, right? And we know from, like, say, balancing equations, for example, that we don't really lose anything along the way in a chemical reaction. Basically, everybody's just rearranged. So the idea here is if we collect up all the CO2 here, pretty much it contains carbon. And the only thing on the reactant side that would contain carbon would be like our unknown substance. So all the carbon that came from our unknown substance would have found its way into the CO2. This will allow us to use the mass of the CO2 that's collected, along with some calculations like we did earlier in this chapter, to eventually get to how much mass of carbon was collected, or how much mass of carbon we even started with, really. Again, all the carbon that we end with had to come from really our organic substance. Now, if we look at the water, same idea with the water here. All of the hydrogen that we collect here in the water, all of that original hydrogen had to originate from also our organic guy here. And that means that we can do some calculations and use the mass of water that was collected to basically figure out eventually the mass of hydrogen that we started with. If I could write here, try that again. Hydrogen. That's a really creative way of writing hydrogen. Let's try that again. Hydrogen. There we go. That's the mass of hydrogen that would be collected, and also, again, the mass of hydrogen that we essentially started with. So through this sort of procedure where you basically burn this organic substance in sort of a closed system, and we'll see a picture of it in just a second, you're able to sort of absorb and collect all this water. You're able to absorb and collect all this carbon. And why is that important? Well, through calculations, we will then know the mass of hydrogen. We will know the mass of carbon. And if we know the mass of the original substance, we can then subtract off the mass of the the mass of the hydrogen that was collected. We could also subtract off the mass of the carbon that was collected. And that will give us the mass of oxygen that was originally there. Any questions on that sort of approach? Now, you may be asking yourself, why can't we just kind of use the CO2 and the H2O to sort of directly figure out, how much oxygen we had? The reason is, in addition to oxygen being in our original guy, we add oxygen as part of the reaction, which means some of this oxygen we got over here and some of the oxygen that we got over here is going to come from this oxygen, which is not part of the original compound. So that's why we have to sort of go with figuring out how much carbon there was, because that was part of the original program there, our substance. Figure out how much hydrogen. And again, conservation of mass here tells us that whatever mass is left over has to be the mass of the oxygen that we originally started with. So that's why we can't sort of directly calculate how much oxygen we collected, because we actually added oxygen, some more oxygen here to the reaction. And thus we don't know, where this guy pretty much ended up. Some could be in here, some could be in here. But what we do know is for sure how much carbon and hydrogen we collected. That's going to allow us to calculate the amount of oxygen. Questions on that there? How are we going to do this? Well, we're going to do this very similar to a calculation we did earlier in the chapter where we use the actual formulas of CO2. So if I look at the formula of CO2, 1 mole of the entire thing will give me 1 mole of carbon. So if you remember, I think we did a problem where we were trying to find how many hydrogens there were. And that's the same idea. We could actually use the formula as a conversion factor. We could do the same thing for hydrogen. And every 1 mole of H2O, there is 2 moles of hydrogen. So that's how we're going to go from how much water we collected, how much CO2 we collected, to just the elements. And at some point, we will have the mass of all 3 elements, the carbon, the hydrogen, and the oxygen. And the good news at that point is then you could actually go do your empirical formula calculation like we did before. So we have to do a little bit more work on a problem like this to get us to how much oxygen we have, how much hydrogen, how much carbon we have. And once we get there, then we can go back and kind of do a traditional sort of stoichiometry problem at that point. Any questions on that there? Okay, so let's go through one here together to kind of see how we would work it out. And this is sort of the setup here. We got basically some oxygen coming in to this closed system. We have our ethanol here. Our ethanol is basically made out of carbon, hydrogen, and oxygen. We're going to heat this up. It's going to basically start to evaporate. It's going to come through here. And through this first guy, we're going to collect all the water. CO2 will be able to kind of continue on. And then when it goes through the second guy, it'll collect all the CO2, basically. And at that point, we've now collected basically the water and the CO2. We see from the experiment here that they collected 22 grams of CO2. They collected 13.5 grams of water. So we'll start with carbon first. So we want to figure out the mass of carbon in our organic sample, in our original sample. So again, all the carbon is going to end up in the CO2. So we'll take the 22 grams of CO2. We need to get the molar mass of CO2, and that is going to be 1 carbon at 12.01 plus 2 oxygens at 16. That's going to give us 4401 grams per mole of CO2. And if we get an answer at this point, we will end up with 0.4999, we'll call it. There we go. I believe, let me just double check here, 22 divided by 44.01. There we go. So we end up with 0.499. We'll go one more, I guess, 89, so we don't round too much, moles of CO2. Remember, though, that we are not interested in CO2. We're actually eventually interested in just carbon. So the reason we needed to convert these guys into moles here is now we can use the actual formula as a conversion factor, and we know that 1 mole of CO2 is equal to 1 mole of carbon. And again, since this is a mole to mole relationship, this is why we had to convert it to moles. And I could do that, I think. So this is going to be 1 mole of the entire thing gives us 1 mole of carbon. That gives us 0.49989 moles of just carbon. Any questions on that part there? Now, remember, we do kind of need the grams of carbon to figure out how much of this original 11.5 sample, which is sitting in here, 11.5 grams, was made up of carbon. So to do that, we would go to the periodic table, we would look up the molar mass of carbon, and that is a 12.01 grams per mole. And if we do all that good calculations there, that's going to be times 12.01. Looks like 6.004 grams of carbon, or we could just round it to maybe 6 grams of carbon. Any questions on that calculation, where any of the numbers came from? Again, the purpose here is to try to figure out how much carbon we collected and also how much hydrogen. Any questions on that?
So 1 mole of carbon and 1 mole of CO2 is the 1 mole of carbon was taken from how many like moles of carbon are in 1 mole of CO2?
Yeah, so it actually was taken directly from the formula, and kind of like what we were talking about with empirical formulas, right? When we do that kind of dividing part, and to get these guys on the bottom, these subscripts, they also represent how many moles there are of each of those guys. So that's why we know 1 mole of the entire thing, there's basically 1 mole of carbon. If we were interested in the oxygen in 1 mole of the entire thing, there would be 2 moles of just oxygen. So we could kind of use the formula as a conversion factor. And that's because technically in the formula, these subscripts represent basically how many moles of that atom there are as well. And that's kind of how we get those subscripts when we do like dividing by the smallest number of moles. It's basically dividing moles by moles, right? And that's sort of where those subscripts come from. And that's why we could kind of reference them as moles.
Thank you.
You're welcome. Other questions on that? Okay. So now we know that out of that 11.5 grams, 6 grams of it is basically was made up of carbon. We could do the same thing for our water now and our hydrogen. So we're going to do a very similar calculation. We're going to figure out the mass of hydrogen in the original sample. And again, all the hydrogen in that original sample is going to end up over here in the water, basically being absorbed. So doing the same calculation, we're going to go 13.5 grams of water. We also need to convert it into moles, so we could do that mole to mole relationship. So water being 2 hydrogens at 1.008 from the periodic table, plus a 16 gives us 18.02 grams per mole of water. And again, I'll get an answer here, and it looks like what I will get is 13.5 divided by 18.02 is 0.749. We'll go one more maybe. 1.7 moles of water. So now that we have this in moles, we can again use the formula for water. And what we see on water's formula is in 1 mole of H2O, there are 2 moles of just hydrogen. So again, using the formula and those subscripts as conversion factors is going to allow us to go from the moles of water that was collected to how many moles of just hydrogen that would be. So 2 moles of H. Timesing that by 2 gets us 1.4983. Come here. Maybe 1.4983 moles of hydrogen. And now, just like we did with the carbon, we could use the molar mass of hydrogen from the periodic table to figure out how many grams that would be. And that's going to be 1.5, we'll call it 1 grams of oxygen in this particular case. Any questions on that calculation there? All right. Now that I know basically how much carbon there is, I also now know how much hydrogen there is in this 11.5 grams. The only other element that should be there is oxygen. So I could take both of those values and use it to figure out how many grams of oxygen was present. Thank you. Can I just pretend O is like hydrogen? They kind of go together. Thanks. There you go. Yeah, so the 18.02, is the molar mass for water. So if we go from the periodic table, it's 2 times 1.008 plus 16 there grams per mole. And again, that's just from the periodic table, adding up all the parts to get to the 18.02. Other questions on that? Okay, so now that I got my carbon, now that I got my hydrogen, now I can find my oxygen there. I got my letters in the right spot, so that's good. What we're going to do is to figure out the mass of oxygen that would be there. We're going to take the mass of the original sample, which was 11.5 grams given to us here. We now know out of that 11.5 grams, 6 grams of it was carbon. We also know that 1.51 grams was hydrogen. And if we do all that good stuff there, we end up with 3.99 grams in the original sample. That's left over basically was how many grams of oxygen there are. Any questions on that there? All right, well, now that we know how many grams of oxygen there are, we know how many grams of carbon there are and how many grams of hydrogen there are. We actually now can do the actual empirical formula problem. We want to convert these grams into moles. We want to divide by the smallest number of moles and do the rest of our empirical formula problem. So this kind of pre-problem here is getting us to a point where we now can actually do the empirical formula part of the problem. The good news is, as well, is you want to kind of think about your calculations you just did, and you want to remember that, you don't want to kind of redo some calculations. So if we look at our grams of carbon and go back one step, we've already calculated how many moles of carbon there are. So we actually have that number. If we actually go back one step for hydrogen, we have that number as well given to us. So really, for empirical formula calculation, we actually have two of the numbers kind of given to us already, or we already calculated it. You probably don't want to go back and sort of recalculate it. Really, the only one we need to then calculate into moles would be the grams of oxygen at this point. I mean, if you went back and recalculated, not a tragedy, but you already sort of have some of these numbers, so you don't want to maybe go back and have to redo it again. So I'm just going to retransfer those numbers to the next page. So we got 0.49989 moles of carbon that we calculated previously. We had 1.4983 moles of hydrogen that we calculated. And now we do need to take the 3.99 grams of oxygen, use the molar mass from the periodic table, which is 16 grams per mole, and divide by it to get us 0.2494 moles of oxygen. And that would be the guy that we need over here. Any questions on that so far? So what I just did basically is equivalent to what we were talking about in our empirical formula problem last time of converting everybody into moles. Now that I have everybody into moles, just like we've done before, we're going to divide by the smallest number of moles, which does appear to be 0.2494, 0.2494, and 0.2494. Again, this is equivalent to going from grams to moles, dividing by the smallest number of moles. Oops, and not hit the thing and get that out of my way. And now if we do that, we will end up with some numbers. And it does look like perhaps we end up with a 2 there on the first one, I think. basically we end up with a 2. We basically end up with a 6, and we end up with a 1 in that particular case. In this particular case, by dividing by the smallest number of moles, we hit pretty much whole numbers there, I think. Divided by 0.2494. There you go. We got all whole numbers, so that would give us our empirical formula of C2H6O, which would be our empirical formula. Any questions on that? So a combustion sort of problem is really like a really traditional empirical formula problem, except that you gotta do a little extra work there to get everybody's grams and stuff like that. Once you get everybody's grams, then you are good to go in terms of actually doing the empirical formula part of the problem. Any questions on that there? This could be something, by the way, the empirical form doesn't really tell us necessarily what it is, you know. By the way, since this is ethanol, this is sometimes also written like this in terms of the formula. And sometimes chemical formulas are written sort of like this, where it doesn't necessarily give you any type of information about how everybody's hooked together. Sometimes they're written like this, which gives you a little bit more information about how it's actually hooked together. And if we were to draw something like ethanol, it looks something like this. It's an alcohol, and it's this part over here, this OH group, that makes it an alcohol. So you can see this guy here gives a lot more information about how it's connected. But if you just count up everybody that's there, that is what you end up with: 2 carbons, 6 hydrogens, and 1 oxygen. So formulas are interesting. Sometimes formulas do really give you a little bit more pieces of information about maybe connectivity and how things are hooked up. But sometimes formulas are pretty basic in the sense of this is what's present in here. Not really going to tell you how it's all kind of put together. Any questions on that there? Okay. Now that we know sort of how to calculate an empirical formula, let's talk about the process that you need to do then to actually calculate the molecular formula. So to calculate the molecular formula, there's really a few things that you need. First off, you need the empirical formula. So it may be given to you in the actual problem. You may have to calculate it like we just did this time and last time. So this may or may not be given to you. The next thing that you need to know is the approximate molar mass of the compound. The good news on that is usually always given to you. So somewhere in the problem, they will yell at you, maybe not yell, but they will tell you, hey, this compound was found to have a molar mass of approximately 200 grams per mole. Or they may even give you a range like, hey, this guy's molar mass is somewhere between 100 and 120 grams per mole. But somewhere in the problem, they will give you that sort of information. They'll give you, somewhere that this is pretty much the molar mass of the compound. The other thing that you need to calculate is the empirical formula's molar mass. So usually number 1 and number 3, you kind of need to calculate it a lot of times. And again, you kind of just do the same process we just did. And what do you do with those numbers? Well, you take the molar mass of the compound that was given to you. You take the molar mass of the empirical formula that you calculated, and it will give you a number. I will say usually this number is a whole number, or pretty close to a whole number. If it's not a whole number, out of all the places, this is a place where you probably could round to the nearest number in this case. So because the molecular formula is really based off of sort of the empirical formula, and it's basically a whole number ratio of it, the one place where you could probably do rounding in every case would be when you're doing this calculation here. If it doesn't hit exactly a whole number, if you got like 4.2, probably 4 is the number that you would use, for it. What do you do with that number? So let's just say, for example, the number that you got was, 3. right? So you're going to get this number. And what does that mean? Well, it means, well, at this point, you will have your empirical formula. So let's just say this was your empirical formula. What you would do with this 3 is basically what it is telling you is your molecular formula is like 3 times as much here of your empirical formula. You would multiply everybody in the empirical formula by 3. So it would end up being A3B6 in this case would be our molecular formula. So what this number really gives you is sort of a factor by which you can multiply the empirical formula by to get you to the molecular formula. You could also, sometimes people will write it like this. They'll take the empirical formula, put parentheses around it, and put the little 3 on the outside. I would say probably 9 times out of 10, maybe even more than that, people will distribute this and really write the molecular formula in this form and not really put the parentheses. But you do sometimes see people sort of do that. So if you need to calculate the molecular formula, you got to first calculate the empirical formula if it's not given to you. You then need to figure out the molar mass of the empirical formula. You need to divide the molar mass of the compound, which is given to you in the problem, and divide it by the molar mass of the empirical formula, and then get your sort of factor by which you should multiply the empirical formula by. Any questions on that one there? All right, why don't you guys give it a try and see what you come up with? So we got something with boron, we got something with hydrogen. Boron from the periodic table, 10.81 grams per mole. Hydrogen from the periodic table, 1.008 grams per mole. All right, take a few minutes and calculate the molecular formula here in this particular problem. The 3 in the last example was just something I made up, but it would have came, for example, by multiplying these two numbers. I just made up the 3. Just you could get a 3, you might get a 2, you might get a 4. You'll get some type of kind of whole number when you do that division on the bottom. And then that number is basically the factor by which you need to multiply the empirical formula by. But the 3 actually I just made up. So we have the grams of boron, we have the grams of hydrogen. We're going to do our normal sort of process here. We're going to take those grams and convert them into moles, and using the molar mass from the periodic table. And if we do that, it looks like 0.5961 moles of boron. We'll do the same thing here for our hydrogen. We will end up with 1.789 moles of hydrogen. At this point, like we've done empirical formula before, we want to divide by the smallest. So it looks like it is the moles of boron here. That's going to give us 1. That is going to give us about 3. So now we have our empirical formula, which is BH3. I'll put a box, even though it's not really the answer here, but that is the empirical formula. Any questions on that calculation there? All right, now that we have the empirical formula, that's one of the 3 pieces of information that we need to actually get to the molecular formula. So one piece of information is obviously the empirical formula. The other piece of information is the approximate or parent molar mass of the compound, which is 30. And the third piece is we need the empirical formula of this guy. So the molar mass, we need the molar mass of that guy of BH3. That gives us 1 boron at 10.81 grams per mole, plus 3 hydrogens at 1.008 grams per mole. That gives us 13.834 grams per mole, which is our molar mass here of our empirical formula. At this point, we take the molar mass of the compound that was given to us. We divide it by the molar mass of the empirical formula, and here we get maybe something like 2.16. Again, in this case, probably close enough on this number here to round. And this is probably the only place where it's good and okay to round in this type of thing. If you got 2.16 up here, you probably shouldn't round. But for the molecular formula part, it's okay. And that means that our molecular formula would be B2H6 in this particular case. And that would be our molecular formula. Or again, you could if you wanted to, and sometimes people will write it sort of as it's two of these sort of BH3 units. Most people will go with this, but you still sometimes see people that write like that. But probably this way would be a better way of doing that. Any questions on those steps there? Okay. Why don't you try another one here and see what you come up with? We have phosphorus. What is the empirical and molecular formula here? Phosphorus is 3097. Oxygen is 16. And see what you come up with here, and then we'll discuss it. Seen on this particular one here. So in this case, we're looking for both the empirical and molecular formula. We're actually given the percentages of phosphorus and oxygen. We're also given sort of the experimental molar mass of the compound. So we're going to start with the empirical formula as it was not given to us. So just like last time, we're given some percentages here. We might want to just kind of quickly take a peek at them, make sure it adds up to about 100%, and just roughly looking, it does appear to add up to 100%. That means we could essentially assume that we have 100 grams of this substance. And what that really just does is it just turns these percentages into grams, the same number. And that means that we would technically have 43.64 grams of phosphorus, which we do want to convert into moles. So we would go to the periodic table. We would divide by 3097. That is going to give us 1.409 moles of phosphorus. We would also then assume that we have 56.36 grams of oxygen. And we would divide by 16 grams per mole of oxygen. And that gives us 3.523 moles of oxygen. So again, just like we've done with our empirical formula before, converting our grams into moles, we then will proceed to divide by the smallest number of moles. This looks like a 1.409 in this situation. That's going to give us a 1 for the phosphorus, and that's going to give us a 2.5 for our oxygen. That means if we wrote our empirical formula, it would be PO 2.5. As we talked about before, this is not good. This is too far to round and stuff like that. So we want to find, again, a factor by which we can multiply this empirical formula by to get all whole numbers. So you could just do trial by error. 2.5 times 1 is 2.5. 2.5 times 2 is 5. So that will do it. That means we're not going to multiply by 5, but the factor we're going to go with is, actually, I should circle the right one there. It is 2 on that side there. Get rid of that box there. So we're going to take that empirical formula. We're going to multiply it by that factor of 2, basically. And when we do, we end up with P2O5, and this would be our correct empirical formula. Any questions on that one there? That is part of the answer. So we got the empirical formula part. We now need to get the molecular formula. So we need 3 things. We have the empirical formula. We also have the molar mass of the compound. So the one last thing that we need is actually the molar mass of our empirical formula. So the molar mass from the periodic table of our P2O5 is 2 times 3097 plus 5 times 16. And I think about a 141.9 grams per mole would do it for us. At this point, we're going to take the molar mass that was given to us in the problem for the compound, which is 283.89. We're going to divide it by our molar mass of our empirical formula, which is 141.9. And not drop the calculator here. Give that a go. 283.89 divided by 141.9. And that's going to give us a factor of basically 2. That means that our molecular formula should be P4 timesing the 2 by the empirical formula, O10 as our molecular formula. Any questions on those calculations there?
Yeah, I have one.
Yeah.
So going back to the 2.5.
Over here? Yeah.
Yeah, I just have a question on why you multiplied it, I guess the first one by 1 and the second one by 2.
I multiplied the entire thing by 2. So this guy was. Are you talking about the 1 and 2 over here? Is that what you're talking about?
Yeah.
Yeah. Oh, so it was just you don't have to do that, but it's just you're trying to like sometimes called trial by error, trying to find a number that you can multiply 2.5 by to get a whole number.
Oh,
So
okay.
if you could just look at it in your head and know, maybe most of us can. If you go L 2.5 times it by 2, we're good. That's basically what this is for.
Okay, gotcha.
Is just to kind of try to find that whole number factor that you can multiply it by.
And wait, how does that help us? Because I was confusing that too.
In terms of
In terms of how does like guessing and finding those numbers help us if they've already given to us from the formula that we worked out with like 43.64 grams of phosphorus or the moles? Because that's where you got those numbers from 1 and 2, right? Or 2.5.
Yeah, it's a 1 and 2.5 from that. The problem is though, when we divided by the smallest number of moles, we didn't end up with all whole numbers. Yeah. So this would not be a correct empirical formula. So all formulas has to have whole numbers for their subscripts. You can't have like a half of oxygen atom basically. So what we need to know is basically a factor to multiply this non-whole number by that will get us to a whole number, because basically back to those kind of laws in the first chapter, everything is kind of put together in sort of proportions and ratios of whole numbers. That's basically how these atoms come together as sort of whole numbers. So since we didn't yield the whole number by dividing by the smallest, we need to figure out the next sort of smallest ratio that we could get that will give us whole numbers for both of them. So obviously if we multiplied this whole thing by 1, we would end up with the same numbers, 1 and 2.5. By multiplying this guy by 2, we then end up with P2 and O5. That's enough to get us whole numbers on both of these guys. And the simplest way to do that, you can multiply it by like a giant number if you want, right, to get a whole number. Like perhaps you could do 4, right? And if you multiply it by 4, you'll get a whole number on both. But remember, the empirical formula is the simplest set of whole numbers. So that wouldn't give you the kind of simplest set of whole numbers to get you there. If you multiply by 4, you then could reduce it down to, down to here, basically to this guy. So we're looking for really a multiple number that we can multiply, sort of the smallest number that we can multiply that by, that will yield us whole numbers for everybody, because that will give us that empirical formula relationship of basically the simplest set of whole numbers that would come together. Questions on that? And it's just an idea if you just go to think about it, like, if we look at just say P1 O2.5, right? So basically, and I'm going to do some really bad drawings here, for every one of these whole phosphorus, right, in this bad drawing, we have, 1 oxygen, 2 oxygens, and like a half a oxygen atom, right? So if we needed to fill in that half of oxygen, we would need another half of oxygen, right? And 2 more. And along with that, half and 2 would be another phosphorus, right? So that's the simplest way to get us to basically all whole numbers would be basically a ratio of 2 of those colored units together, 2 phosphorus and 5 oxygens together. Other questions on that? It was sort of a not terrible drawing, I suppose. Now, this is one approach and one way to calculate the molecular formula, and it's a very common sort of approach and way to calculate the molecular formula. But sometimes people, especially when you're given the percentages of everybody, sometimes people will kind of work it the opposite way. So what I mean by that is we sort of worked it from empirical formula to molecular formula. You could, because you have the percentages, kind of work it from molecular formula back to empirical formula. I know I missed the empirical formula. We'll just do a U-turn. So we can actually work it the opposite way. So I'll just show you sort of that approach as well. And again, you can kind of choose whichever way you kind of like to do it. So let's say, for example, that we took the same question that we were working on here in this problem. And basically what we had was 43.64% by mass phosphorus. And we had 56.36% by mass oxygen. And the molar mass of this whole thing was basically 283.89 grams, right? So really what these are the percentages by mass of each of these elements in here. So basically what we're saying with this number is basically made up of phosphorus and oxygen, sort of mass of phosphorus and oxygen. So we could take the percentage of phosphorus and convert it into a decimal by dividing by 100. And if we do that, that converts it to 0.4364, which is basically 43.64%. And if we multiply it by the molar mass of this compound, because again, basically what that number means is 43% of this 283 grams is made up of phosphorus, would tell us that we would have about 123.89 grams of phosphorus in the 283 grams. Any questions so far? So this is kind of like the percent composition sort of calculation that we did, right? Now, what is 123.8? Yeah, question? No. Okay. What does 123.89 grams of phosphorus represent in terms of moles? We could then convert it into moles by using the molar mass of phosphorus, which is 30.97 grams per mole of phosphorus. And we end up with 4 moles of phosphorus. Now that number might look familiar to you from what we just calculated, but let's do the same calculation for oxygen. Basically, out of that 283 grams, 56% of it is oxygen. So converting our percentage of oxygen into a decimal, we could times it by 283.89 grams. And that tells us that we have about 160 grams of oxygen in there. What does that represent in terms of moles? Dividing it by 16 grams per mole gives us 10 moles of oxygen. What do those two numbers represent from what we just saw on the previous slide? That is the molecular formula, which would be P4O10. So because you have the percentages, you could actually start and calculate the molecular formula first. What would be the benefit of that? Well, you could then reduce this molecular formula down to the empirical formula. This means that there's 4 moles of phosphorus for every 10 oxygen atoms. That is the same relationship as 2 phosphorus for every 5 oxygen, which means the empirical formula would be P2O5. So this is another approach to this type of problem because you have the percentages of everybody, you could actually start by calculating the molecular formula first, and then just simply reduce that down to the simplest whole number ratio to get to the empirical formula. Or you could do the opposite. You start with the empirical formula like we did on the previous one and go to the molecular formula. Questions on that approach there?
So in this case, you reduced it all the way down, but the other one you didn't.
Well, yeah, in this case, we started with the molecular formula, which means, remember, the molecular formula is not necessarily always the simplest whole number ratio. That's basically the empirical formula. So now that we got to the molecular formula, we basically could reduce it down. Basically, what we're doing is we're dividing the molecular formula by 2, right? Because we divide those subscripts by 2, that gives us all whole numbers, and that reduces us down to the empirical formula. The other way, we're kind of doing the opposite approach. We're taking the empirical formula and then we're multiplying it by 2, right? So in this case, we're going kind of backwards. We're dividing by 2 to get back to the empirical formula. Going from the empirical formula to the molecular formula, we need to multiply by 2. So it's just sort of an alternative approach to this type of problem. Some people like to do it this way because they have the percentages. Some people like to do it the empirical formula first. They both, if you do it correctly, should get you to the same answer. And it's your call, whichever way you want to kind of do that. Any questions on that particular one there? This way, you could see we maybe avoided the ending up with 2.5 and trying to figure out the proper number to multiply it by. We just need to figure out a number to divide everybody by, which might be easier for some people. But again, they both should end up the same way. Any questions on that one? All right, now that we're in a good roll on these, let's try one more here. Let's do some vitamin C. Carbon, hydrogen, oxygen. What's the empirical and molecular formula? Carbon is 12.01. Hydrogen is 1.008. And oxygen is 16. All right, see what you come up with. That we have 100 grams here. And like I said before, that pretty much just keeps the numbers the same. So that would be 40.9 grams of carbon. We obviously want to convert everybody into moles. So from the periodic table, 12.01 moles per gram. Looks like it gets us 3.41 moles of carbon. That would also give us 4.58 grams of hydrogen divided by 1.008 grams per mole of hydrogen. Looks like we get 5.54, I'll spit that out, 5.54 moles of hydrogen. And lastly here, 54.5 grams of oxygen divided by 16 grams per mole. And looks like we got 3.41 moles of oxygen. So again, the same sort of approach that we've done in previous problems here. We're going to convert everybody into moles. We're now going to take the smallest number of moles, which looks like the same number here, 3.41. We're going to divide everybody by that number. That's going to give us approximately 1.33, and approximately 1 here. Which means, again, if I wrote my empirical formula based off of what I just got, I would have C1, H1.33, and O1. As we just spoke about before, this is problematic because, again, you can't have like a 33 1/3% of an atom hanging out there. So here, again, we want to figure a factor in which we can multiply not just the 1.33 by, but everybody in the formula by to yield us a whole number. We're looking for the simplest number that will do that for us. And again, that's where sometimes people just, and if you know it in your head, you don't necessarily have to do this, but, people just go 1.33 is 1.33, obviously. If I took 1.33 and multiplied it by 2, that's 2.66. Close to a whole number. 1.33 times 3 is 3.99. That's fairly darn close to 4. So we will go with this factor of 3 to multiply our empirical formula by. And again, that 3 should yield us pretty much the simplest way to get to whole numbers. So if I take this guy, basically and multiply everybody by 3, gives me C3H4O3. And this would be my empirical formula. Question on that there. Once we have the empirical formula, just like we talked about before, we also have the molar mass of the compound given to us. So we do need to get the molar mass of the empirical formula, and that would be 3 times 12.01 plus 4 times 1.008 plus 3 times 16. Obviously, we'll be adding all those together. 8806 looks like a winner on that one. And that is the molar mass of our empirical formula. So taking the molar mass of the compound given to us, divided by the empirical formula's molar mass, giving us approximately 2. This 2 is the factor we multiply the empirical formula by to get us to the molecular formula. And that means our molecular formula would be C6H8O6. And that should be our molecular formula. Any questions on any of those steps there? And again, you could have done the other approach there and started with the molecular formula and reduced it down. And again, since we got a few minutes here before we're done, I'll show you that since this is the last example anyways. So again, if you kind of did it in the opposite approach, starting with the molecular formula and then taking yourself this way, just to kind of show you what that would look like if you like. Again, here we had 40.9% carbon. We had 4.58% hydrogen, 54.5% oxygen, and the molar mass of the compound, 176.13. So same things we did before to figure out the moles of carbon in the molecular formula. We would take the percentage and convert it into a decimal. So multiply or divided by 100. We would multiply that by the mass of the compound. And basically what that is telling us is how many of those 176 grams is carbon. And it looks like we get something like 72.03, I want to say 2 maybe grams of carbon, just to make sure here. Let me make sure. Come here, maybe 0.409 times 176.13, 72.037, that last number is, not 2. And since that is how many grams of carbon, we then can convert that into how many moles of carbon would be in our molecular formula in this case. And that moles of carbon is about 5.998, which is close enough to round to 6 moles of carbon. We would do the same thing for hydrogen, 0.0458, which is 4.58% converted into a decimal, times 176.13, gets us 8.0668 grams of, this was hydrogen, I believe. And dividing that by the molar mass of hydrogen, 1.008 grams per mole, yields us 8 moles of hydrogen. And lastly here, moles of oxygen would be 0.545 times our 176.13, going to get us 95.99 grams of oxygen, dividing that by 16. from the periodic table tells us we get something like, again, 5.999. So again, when you gain numbers like this, that is close enough to round to 6 moles of oxygen. Again, in this approach, we're going with the molecular formula first. So when we get these numbers here, that will tell us that our molecular formula is the C6H8O6, just like we found on the previous slide. Any questions up to that point there? At this point, it's now a point of just reducing this down to the simplest set of numbers. So that's basically 6 carbons to 8 hydrogens to 6 oxygens. If you divide everybody by 2, that's the same thing as saying 3 carbons for every 4 hydrogens for every 3 oxygens. And that is as low as you could go and still end up with whole numbers. And that is where we can then get our empirical formula from. So again, you can see both approaches ends up in the same spot. It's just whether you want to kind of go from empirical to molecular, or you have enough information to go from molecular back to empirical. Again, this works because this is really all based off of the percent composition by mass and how these sort of atoms come together. They always come together in basically whole number ratios with each other. And that's how we could kind of work these problems either way, really. Any questions on calculating molecular formulas, empirical formulas, one way versus the other? Any of those questions? All right, that then actually wraps up chapter 5. What we will be going next after chapter 5 is back to chapter 3 for the very last section of chapter 3, which is all about nomenclature. So I guess on Tuesday, it will be big naming day in lecture. So we'll do all of the nomenclature stuff there in lecture on Tuesday.